Lithium-Ion. It is the battery inside almost every phone, laptop, and electric vehicle sold today, and its rise came from solving problems that older batteries never could. Before it existed, rechargeable batteries lost capacity on their own, suffered from memory effects that permanently shrank how much charge they could hold, and were heavy for the energy they stored. Sony brought the first commercial lithium-ion battery to market in 1991, and it spread quickly because it offered more energy at less weight, held its charge longer between uses, and survived hundreds of charge cycles without serious degradation. The chemistry works by moving lithium ions between two electrodes during charging and reversing that movement during discharge. The electrodes themselves do not chemically transform, which is what allows the battery to be recharged so many times. Over years of use, it does lose capacity gradually, and it carries a small risk of fire if punctured or exposed to extreme heat. But no rechargeable battery technology has matched its balance of performance, cost, and practicality at scale. Lithium polymer. Most people have used one without ever knowing the name. Lithium polymer is a variation of lithium-ion that replaces the liquid electrolyte inside with a soft gel or solid polymer material. That change allows the battery to be made in thin, flexible, and irregular shapes rather than the rigid cylinders or rectangles that standard lithium-ion requires. Smartphone designers adopted it quickly because it let the battery fill the exact internal shape of a device rather than forcing the design around the battery. Drones, wireless earbuds, and ultra-thin laptops all depend on the same flexibility. The energy density is slightly lower than standard lithium-ion in most cases, and the cells are more sensitive to physical damage, but the freedom of form it offers make it essential to modern compact electronics.
Nickel metal hydride. Before lithium-ion took over, this was the rechargeable battery the world ran on. Through the 1990s and into the early 2000s, nickel metal hydride batteries powered camcorders, portable game consoles, early laptops, and the first hybrid cars. The Toyota Prius used a large nickel metal hydride pack for years before lithium-ion became affordable enough for automotive use. Compared to the older nickel-cadmium batteries they replaced, they stored more energy and removed cadmium from the equation entirely. The weaknesses were always present. They discharged on their own relatively quickly, even when sitting unused, generated more heat during charging, and were heavier for the energy they stored. Today, they survive mostly in AA and AAA rechargeable batteries sold for everyday household use, where lower cost and tolerance for casual charging habits keep them relevant.
Nickel-Cadmium. This is where the modern rechargeable battery story begins in a practical sense. For several decades, nickel-cadmium batteries were simply what a rechargeable battery was. Power tools, cordless phones, two-way radios, and early portable electronics all ran on them. The chemistry is durable and tolerates being fully discharged and recharged repeatedly without the kind of damage that ruins other battery types. The problem that followed nickel-cadmium everywhere was the memory effect. Charging the battery before it was fully drained caused it to gradually lose usable capacity, behaving as though the point where you usually plugged it in was actually empty. Users had to drain it completely on a regular basis just to maintain performance. The cadmium inside is also highly toxic and difficult to dispose of safely, which eventually led to restrictions on its use across much of the world.
If you're enjoying the video so far, leave a like and subscribe for more.
Lead acid. No battery technology has been in practical use longer, and none has remained more consistently present despite being surpassed in almost every performance category. Gaston Plante invented it in 1859, and the fundamental chemistry has changed very little since. A lead plate and a lead dioxide plate sit in a sulfuric acid solution, and the reaction between them produces electrical current. The battery is heavy, large relative to its energy output, and poorly suited to portable use. What it offers instead is the ability to deliver a very large burst of current in a very short time, which is exactly what a combustion engine needs to start. That single capability has kept lead-acid batteries under the hood of nearly every petrol and diesel vehicle ever built. They also appear in backup power systems and uninterruptible power supplies where weight is not a concern. They are cheap, reliable, and recyclable at a very high rate, which keeps them present in a world that has otherwise moved well past them. Solid state. Every battery type covered so far uses a liquid or gel electrolyte to carry ions between electrodes. Solid-state batteries replace that liquid with a solid material, and that single change has the potential to address several of the most persistent problems in battery technology at once. A solid electrolyte does not leak, does not ignite, and does not degrade the electrodes around it the way liquid electrolytes do over time. Solid-state batteries can theoretically store more energy in the same space, charge faster, can last significantly longer than lithium-ion. The reason they are not yet in consumer devices is manufacturing. Producing a solid electrolyte that is thin enough, stable enough, and conductive enough to work reliably at commercial scale remains extremely difficult and expensive. Toyota, Samsung, and several dedicated battery companies have been working toward this for years, with some early versions already used in medical devices and specialized electronics. The broader market is still waiting. Sodium-ion. Lithium is not evenly distributed around the world, and the growing demand for batteries has made its supply a serious concern. Sodium-ion batteries use sodium instead of lithium as the ion that moves between electrodes during charging and discharging. Sodium is one of the most abundant elements on Earth, found in ordinary salt, and sourcing it carries none of the complications attached to lithium mining. The chemistry works on the same basic principles as lithium-ion, which means existing manufacturing infrastructure can be adapted rather than rebuilt from scratch. The current limitation is energy density. Sodium-ion stores less energy per kilogram than lithium-ion, making it less suitable where size and weight are tightly constrained. For large stationary storage and lower-cost electric vehicles where range is less critical, it is already entering the market. CATL, the world's largest battery manufacturer, began commercial production of sodium-ion cells in recent years. Fuel cell. A fuel cell does not store energy the way every other type on this list does. It generates electricity continuously through a chemical reaction, as long as fuel is supplied. Hydrogen fuel cells combine hydrogen gas with oxygen from the air, producing electricity and releasing only water vapor as a byproduct. The appeal is clear. Hydrogen can be produced using renewable electricity. Refueling takes minutes, and the output of the reaction is clean. Toyota's Mirai and Hyundai's Nexo are built around this technology, and it is more established in buses, trains, and heavy freight where hydrogen tanks matters less. The challenge is infrastructure. Hydrogen refueling stations are scarce in most parts of the world, and producing hydrogen cleanly at scale remains costly.